Norway has a long tradition and experience in dam construction for hydroelectric power projects and water reservoirs. Traditional dam construction has been either cement concrete dams or some kind of embankment dams. Embankment dams are often preferred due to costs, environmental and security reasons. A central watertight section or core gives the highest protection against damage caused by acts of war or sabotage. Traditionally, the central core is built of clay or moraine material. Early in the 60s, the idea of applying asphalt concrete as the central core of embankment dams was developed. A properly designed and built dam with asphaltic core is maintenance-free, as the performance records show. Korsbæk og Lork, also known as Kolo, a subsidiary of Veidekke ASA, is one of the major asphalt paving contractors in Norway. Over the last 15 to 20 years, the company has been subcontractor and supplier on the asphaltic core sections on 10 embankment dams, most of them in Norway, but also internationally. We've been involved from the extreme north on the Svartisen Glacier hydropower project in Norway, close to the Polar Circle, down to South Africa at Greater Ceres Dam near Cape Town. The technology, equipment and production technique have developed considerably over the years. The concept is economical and a very competitive alternative to traditional design. This is a profile of the dam showing the watertight asphaltic core or wall in the centre. The asphaltic core with the supporting filter is built simultaneously with the rest of the dam. Asphaltic concrete cores permit impounding during construction, allowing potential seasonal water to be collected prior to full completion of works. The construction starts with a concrete plinth at the bottom of the dam. The plinth must be properly cleaned by washing with hydrochloric acid and water or sandblasting, and finally with compressed air. Asphalt mastic is applied to the concrete surface to secure adhesion towards the first layer of asphaltic concrete. At Ceres, we also built a seepage collector wall downstream to record possible seepage through the core, separating this seepage from possible leakage underneath the dam. At the bottom of the dam and at the abutments, we apply hand placing technique. Quality control shows the same high standard as where paver placing of the core is applied. When the horizontal base of asphalt has been established, the paver can be put to work. The paver is a traditionally hydroelectrically driven crawler paver with a specially manufactured screed. The width of the screed varies depending on the height of the dam. The asphalt mix is led through a built-in funnel behind the screed, and the filter material is mechanically placed as a transition zone. The thickness of each layer has usually been set to 20 centimetres, but we're developing methods to increase the thickness to improve production output. The core machine is equipped with a laser system to control the thickness and level of each layer. From the rotating laser, the signals are received on the paver, and the thickness of the filter coinciding with the core is automatically adjusted as the paver moves forward. Correct level is also controlled from the operator's cabin. The paver can be operated with extreme precision, guided by a centerline metal string, visual on a display or screen in front of the operator. In front, the paver is equipped with a gas-fired infrared heating system to evaporate any surface moisture, as well as heating the previous layer to ensure a firm, seamless adhesion to the next layer. This equipment and technology has made asphalt as core material less dependent on weather conditions than is the case with clay or moraine. In rainy and cold mountain areas, we get a better production output, and the annual production season will be prolonged. Accordingly, the owner's total construction costs will be reduced. The placing of asphalt is systematically controlled. Vital parameters including compaction, permeability, Density, amount of bitumen, voids content, etc. are determined and reported daily. Temperature during compaction is of utmost importance. A non-destructive test method for daily control of compaction and voids content is by means of a nuclear gauge. This control can be done on each layer, and the method is a supplement to drilled cores, especially when progress schedule demands a continuous production of the core. The asphalt mix is produced on a modern batch plant, which is automatically controlled. The asphalt core and filter zones are compacted by 3 rollers. The order of rolling and the number of passes is of great importance to ensure proper compaction and correct form of the core. The visual control on the workability of the mix and how it takes compaction is an important part of the craftsmanship and experience we've gained over the years. The asphalt mix is transported from the asphalt plant nearby using specially designed hydraulic buckets. Filter material is loaded in the machine with an excavator. The machinery has a practical average capacity of 140 cubic meters asphalt mix per day, which is equivalent to 1,400 meters working length per day. Today we've reached the situation where asphalt core is economical and the best alternative by several standards, even when more rain is found locally. From an environmental point of view, this can mean avoiding visible moraine borrow pits in the surroundings of the dam or reservoir. Asphalt is an elasto-viscoplastic material which can sustain differential foundation settlements and dam distortions without cracking. Embankment dams with flexible asphalt concrete cores are, due to these quality features, very earthquake resistant. Inside the body of the dam, the asphalt exists under near ideal conditions, and the core will remain as a flexible and impervious membrane. Asphalt will behave as a self-healing material if any movement or cracking should occur. Bituminous construction materials have been proven to be non-harmful to drinking water sources, like in this freshwater reservoir in Jersey, where we constructed the asphalt core in 1990-91. Drilled cores from the cooled asphalt is the most commonly used documentation for in situ voids content. The cores are drilled to a depth of 50 centimeters. It's important that the asphalt is cooled and cured to a certain degree to avoid any disturbing of the specimen and to get a correct recording of the void's content. The cores are pulled out, cut into bricks and marked as to exact location and depth. The specimen shown proves clearly that the various layers adhere completely into the previous one. There's no visual indication as to where the layers go into each other, as pointed out with the knife. Measuring and recording of the void's content is done at the laboratory. By weighing the mass in air and water, calculations give the densities, and hence the void's content is worked out as the main quality documentation. Triaxial testing can be done as part of the laboratory methods employed for various purposes, like testing mix design, and how the asphalt concrete behaves as to stability and flexibility properties expressed in stress and strain parameters. The Greater Series Dam in South Africa was built in 1997-98 and is the first asphalt core dam of this design in Africa. The consultants were Stefan, Robertson and Kirsten. We'll let Dr. Gary Jones, Senior Partner of SRK, give a brief description of the decision-making on this project and their experience with the technology and contributions we've rendered the project.
This dam is a replacement for an earlier dam that was almost in precisely the same place. The original dam was built in about 1948 and was about 20 meters high. Over a period of time it deteriorated, and particularly because there was an earthquake in about 1969, and that caused some damage.
Because of the possibilities of another earthquake and with expected differential settlements for the dam, the consultants wanted a concept with flexible materials. Furthermore, to achieve the fast-track project in need of irrigation water, they looked for untraditional building methods, independent of weather conditions. The answer was an asphaltic core embankment dam, and Colo was invited as advisor in the planning stage. Later, Colo, in joint venture with Colas, was nominated subcontractor on the asphalt works. The combination of advisor and contractor, even through the construction period, is rather unusual. Notwithstanding, the consultants expressed their satisfaction with Colo as a knowledgeable, experienced and disciplined contractor. Norwegian Geotechnical Institute, NGI, has long experience as professional advisors and consultants on embankment dams internationally and are recognised worldwide.
One of the first things we did when we decided that this was the correct technology for us or the correct solution for this site, we then made contact with Professor Høeg.
The former head of the institute, Professor Kåre Høeg, is very active on the international scene for large dams and is president of ICOLD. He's published a number of papers and ICOLD bulletins on the issue, and the book, Asphaltic Concrete Cores for Embankment Dams, in close cooperation with Statkraft and Colo. The Veidekke Group built our first asphaltic core dam at Storevatn in Norway, starting in 1982. We've now completed 8 more dams, including the Queens Valley Dam in Jersey, Greater Ceres Dam in South Africa, and Storglomvatn Dam in Norway, the world's highest dam with asphaltic core, 125 metres. At present, we're involved in the Maopin Sea Dam, a 3 gorges project in China, as suppliers of the specialist equipment and as advisors. With considerable experience of civil works nationally and abroad, and asphalt in particular, Colo is ready to assist with necessary know-how, technology and specialised machinery in the construction of asphalt core dams. We are prepared to undertake work as advisors and contractors on this concept in close cooperation with specialised consultants.